Welcome to the boiling oil paradox, where we'll discover why oil with a higher boiling point makes food less greasy. This seems counterintuitive at first. How can a hotter liquid make food less greasy? Let's explore this fascinating physics. First, let's understand what boiling points actually mean for water and oil. Water boils at 100 degrees Celsius at standard atmospheric pressure. Most cooking oils have boiling points between 200 and 300 degrees Celsius, much higher than water. This graph shows the dramatic difference in boiling points. Oil can reach temperatures 2 to 3 times higher than boiling water. Here's the paradox. If oil is hotter and literally what we're frying in, shouldn't food absorb more oil? Let's find out why the opposite happens. The key to understanding this paradox lies in the water content of food. Most foods we fry, like potatoes or chicken, contain between 60 and 95% water by weight. Imagine a piece of food as a collection of water molecules trapped inside a structure. These water molecules are crucial to the frying process. A potato, for example, is about 80% water by mass. So what happens when we drop this water-rich food into oil that's heated to 180 degrees Celsius? Now let's explore the critical physics that makes everything work. Let's consider what happens when oil is too cold, say below 100 degrees Celsius. When oil is below 100 degrees, the water inside the food doesn't boil. Oil simply soaks into the food, making it greasy and soggy. But when oil is at the ideal frying temperature between 160 and 190 degrees Celsius, something magical happens. At this temperature, water inside the food rapidly boils, creating steam that pushes outward, preventing oil from entering. The water undergoes a phase transition from liquid to gas when temperature exceeds 100 degrees Celsius. Let's understand the pressure dynamics that create this protective barrier. The pressure of the steam pushing outward is greater than the pressure of the oil trying to enter. This steam acts like an invisible shield, constantly pushing outward and blocking oil from soaking into the food. The green arrows show steam pushing out with great force, while the red arrows show oil being kept at bay. Those bubbles you see when frying aren't oil bubbles. They're water vapor escaping from the food. Let's work through a real numerical example with a French fry. Consider a single French fry with a mass of 10 grams. Since potatoes are 80% water, this fry contains 8 grams of water. 8 grams of water equals 8 milliliters of volume. Now, when this water boils and converts to steam, something dramatic happens to its volume. Steam occupies approximately 1,600 times more volume than liquid water at atmospheric pressure. So our 8 milliliters of water becomes 12.8 liters of steam. That's enormous. This dramatic volume expansion creates enormous outward pressure that effectively blocks oil penetration. Let's examine the energy requirements for this water-to-steam conversion. The heat energy required equals mass times the latent heat of vaporization. The latent heat of vaporization for water is 2,260 kilojoules per kilogram. For our 8-gram water sample, we need 18.08 kilojoules of energy to convert it all to steam. Where does all this energy come from? From the hot oil surrounding the food. This is why the oil must maintain a high temperature to continuously supply the energy needed to keep generating that protective steam barrier. What happens to oil temperature when we add food? The temperature drop equals the heat absorbed, divided by the oil mass, times its specific heat capacity. Let's say we have 1 liter of oil at 180 degrees Celsius. Oil has a mass of about 920 grams per liter and a specific heat capacity of 2 joules per gram per degree Celsius. Adding our single fry drops the oil temperature by about 10 degrees Celsius. This is exactly why we shouldn't overcrowd the pan. Too much food drops the temperature below the critical threshold. One piece of food. Oil stays hot and food fries perfectly. Too many pieces. Temperature drops, steam barrier fails, food gets greasy. Now let's talk about what happens at the food surface during proper frying. When oil is hot enough, it triggers the Maillard reaction at the food surface. The Maillard reaction requires temperatures above 140 degrees Celsius. This creates a golden, crispy crust on the outside while the interior stays moist. Perfect texture. This crust becomes an additional physical barrier that prevents oil from entering the food. But wait, if hotter is better, why can't we just use extremely high temperatures? When oil temperature exceeds 190 degrees Celsius, several problems occur. First, the outside of the food burns before the inside has time to cook properly. Second, the oil begins to smoke and chemically degrade, producing unpleasant flavors and harmful compounds. Most vegetable oils have a smoke point around 230 degrees Celsius. This graph shows the three zones. Too cold results in greasy food, perfect temperature gives crispy results, and too hot causes burning. Let's examine when oil actually gets absorbed into food during the frying process. During active frying, when the steam barrier is working, oil absorption is minimal, maybe only 5 to 10%. But here's the critical insight. Most oil absorption happens after you remove the food from the oil. Research shows that about 80% of oil absorption occurs during the cooling phase. This graph shows oil content over time. Notice the sharp increase during cooling. Why does this happen? Because as the food cools, the water vapor condenses and contracts. Steam condenses back into liquid water as temperature drops. This condensation creates a partial vacuum inside the food that literally sucks oil inward. Now let's apply this knowledge to practical frying techniques. Rule number 1. Always use a thermometer to maintain oil temperature between 160 and 180 degrees Celsius. Rule 2. Never overcrowd the pan, which would drop the temperature below the critical threshold. Rule 3. Drain food on a wire rack, not paper towels. Wire rack allows steam to escape freely, preventing vacuum formation. Paper towels trap steam and create that vacuum effect. Rule 4. Serve fried food as soon as possible while the steam barrier is still somewhat active. Different foods behave differently based on their water content. High water content foods like potatoes create the strongest steam barriers. Battered foods have less water, but the batter itself provides protection. The relationship is clear. Higher water content leads to a better steam barrier, which leads to less oil absorption. Let's summarize how we've resolved the boiling oil paradox. Oil's high boiling point allows it to reach temperatures well above 100 degrees Celsius. This high temperature causes the water inside food to boil rapidly. The resulting steam creates a powerful outward pressure that prevents oil from entering the food. If we use lower temperatures, there will be no steam barrier, and oil would simply soak into the food. And that's how we solve the boiling oil paradox. Hotter oil paradoxically makes less greasy food through the physics of phase transitions. The brilliant insight is this: it's not the oil that makes fried food crispy and non-greasy, it's the water escaping as steam. We can think of perfect frying as a balance between high heat, water content, proper timing, and quality oil.